Thank you. Welcome to the workshop. I'm Ken Johnson. I'm a senior scientist at the Monterey Bay Aquarium Research Institute. MBARI is a nonprofit private research institution funded by the David and Lucille Packard Foundation with a mission to develop better instrument systems and methods for research in the ocean. I want to especially thank the National Science Foundation, both for helping sponsor the workshop and for having sponsored much of the work that I'm going to speak about today. Very brief outline of my talk. I'm going to give you an introduction to chemical sensors and profiling floats, several science examples that connect to some of the topics of this workshop: fisheries, carbon budget verification, forecasting, and development of a sustained global observing system. So floats with chemical sensors have been operating for about the last 20 years, following a cycle much like Toshio Suga showed you, profiling parking at 1,000 meters for typically 5 to 10 days, then descending to 2,000 meters and collecting a profile. The initial efforts were relatively small-scale science experiments, which led to this workshop that Hervé mentioned that took place in 2009 to look at the prospects for developing a global array. And one of the conclusions of this workshop was that the next step was to develop regional basin-scale arrays. And so in 2014, the SOCOM program, Southern Ocean Carbon and Climate Observations and Modeling, SOCOM program, was initiated, led by Jorge Sarmiento at Princeton. This program has completed 6 years of operation to instrument the Southern Ocean, deployed 204 profiling floats with oxygen, pH, nitrate, biooptical sensors. It was recently renewed for 4 more years and 120 floats. Has been very successful with well over 100 research papers coming from it, and has served as a model for the basin scale program. So the following examples will come from SOCOM as well as several other science programs. And again, I'd like to acknowledge the National Science Foundation, Office of Polar Programs, NOAA, and NASA for contributions to this. So as Hervé noted, there are now a set of 3 operational biogeochemical floats, with the 4th coming in 2002. These floats all carry optical oxygen sensors, can carry optical oxygen sensors, UV optical nitrate sensors, and ISFET pH sensors. These latter 2 nitrate and pH sensors were developed at MBARI. One of the questions that is often asked is I'm going to try, and mine seem to be set on automatic advance, which I don't want, but we'll just fight that. One of the questions often asked is the data of sufficient quality? And in the SOCOM program, we've made a distinct effort to validate the quality of the data. These plots show float oxygen versus measurements made on board ship by classical high quality techniques. Same for nitrate, same for pH, with well over 1,000 measurements, comparisons for each of these parameters. And there is essentially almost no bias in oxygen, less than 1 micromole per kilogram, very little bias in nitrate, very little bias in pH. The measurements after passing through quality control indeed are of high quality. We make the argument that in fact this quality lasts over the life of the float with attention paid to quality control. So to look at the data, here's one example of nitrate measured on profiling floats near the Hawaii Ocean Time Series Station. Nitrate, of course, is a key nutrient that enables phytoplankton growth. The profiling float observations here, 0 to 300 meters, 8 years of data are compared to the monthly measurements made from ships at Hawaii. And you see a distinctly different view of nitrate in the ocean and the processes that supply it to the euphotic zone. The floats show distinct episodic events that are occurring throughout the entire record. The ship-based time series is much more muted and smeared and does not really reveal the events. Kara Wilson's talk in the fisheries session next week will show you an example of the effect of events like this on the ecosystem. And this initial work was published in Nature in 2010. Another example of nitrate is work done by Mariana Biff, who was a graduate student at Miami, now a postdoc at Mabari, but this was work done as a graduate student, looking at an array of profiling floats with nitrate sensors in the Gulf of Alaska. Each year, nitrate is depleted as phytoplankton grows with considerable interannual variability. In 2014, 15, into 16, there was a warm event. It was known as the warm blob in the North Pacific. You see it here in the temperature record, which extends from 2008 up to the present, 2020. During the warm blob, upward transport of nitrate as well as heat cold were limited. Nitrate is depleted, and as Mariana points out, if you have 2 years of this depletion of nitrate in a row, leads to significant ecosystem effects, affects phytoplankton productivity, led to a reduction in zooplankton, impacted fisheries, and all the way up to causing the death of millions of seabirds. This warm blob recovered in 2018, but has since reinitiated and is even more intense, and Mariana predicts even more ecosystem impacts. Another application of profiling float data is the use of the float pH sensors to look at air-sea flux of carbon dioxide related to carbon budget verification. So we can take the float pH measurements, we can take empirical estimates of alkalinity derived from shipboard measurements and then computed using float temperature, salinity, and oxygen to, compute the partial pressure of CO2 in the surface ocean. This was work done by Nancy Williams, then a graduate student at Oregon State University, now an assistant professor at South Florida. And Nancy points out that we can compute the partial pressure of CO2 with good accuracy and understanding the error limits on the data. Allison Gray, then a postdoc at Princeton, now at the University of Washington, took this data in the Southern Ocean, the SOCOM program, and computed the air-sea flux of CO2 in zones from the subtropics down to the ice-covered zone, and compared to the ship-based measurements. The float values in each panel are shown as the colored solid line. The ship-based measurements are the dashed or dotted lines. The floats agree so this is the annual cycle, January to December. The floats agree with the ship-based measurements in summer when there are many ships, but in winter, particularly in the Antarctic Southern Zone, the float-based estimate diverges considerably in winter from the ship-based measurement. These values are positive, which is now a flux from the ocean to the atmosphere. And this is a process not seen in the ship-based data, primarily because there just have been few ships in that region in the winter. Seth Bushinsky, also a postdoc at Princeton, now at the University of Hawaii, then took more of this data, merged it with the ship-based data, and compared the differences in fluxes from the float-based measurements, the ship-based measurements, and a merged product of both of them to look at the cause of the biases in the two sets of data, and comes to the conclusion that much of the difference between the float and the ships is really the spatial distribution, and the best observing system is really merging both products, floats and ships. And this is the path forward to improved observing system for air-sea flux of CO2, the continuous presence of floats combined with the infrequent but higher accuracy ship-based observations. Now, as we think about forecasting in the ocean, predicting the future, I'd like to show one example from the oxygen minimum zones of the Arabian Sea and the Bay of Bengal. In the Arabian Sea, nitrate is lost in the oxygen minimum zone as bacteria consume nitrate and convert it to nitrogen. The Arabian Sea is a globally significant sink for nitrate in the world ocean. Loss of nitrate in the OMZ of the Arabian Sea is an important control on global ocean productivity. The Bay of Bengal has somewhat similar conditions, but does not lose nitrate. And the question is, why does the Bay of Bengal not lose nitrate? And could it possibly transform over in the future to a system like the Arabian Sea and lead to even more loss of nitrate in the ocean? So here we have the mean of all ship observations in both the Arabian Sea in red and the Bay of Bengal in blue from the World Ocean Atlas at the US National Oceanographic Data Center. Very similar profiles when you take the mean of both systems from the ship-based observations. If we look in the oxygen minimum from an array of profiling floats that have been deployed by Argo India, we see quite a different picture. Here is time 2012 to 18, oxygen levels in the core of this oxygen minimum zone. In the Arabian Sea, we see that the oxygen is essentially the bulk of the time set at 0, a histogram of the data. Most of the oxygen data here is set at 0. In the Bay of Bengal, there's much more variability in the oxygen, although still at levels lower than we see in the mean of the shipboard data. But the Bay of Bengal has, although its levels are extremely low, they're not 0. They are set a few micromole per liter above 0. This is high enough to inhibit the bacterial process that leads to nitrate loss. And the question, the forecasting for the future, could the Bay of Bengal ever transition from this condition over to here? It looks like these events are driven by ocean eddies that carry oxygen into the Bay of Bengal. So this fundamentally becomes a question of ocean physics. So final process that ties together fisheries, carbon budgets, forecasting is primary production in the ocean. Today, our best estimates of global primary production come from satellite-based observations of ocean color that are combined with measurements of phytoplankton photophysiology to produce these really detailed maps of primary production in the ocean at the global scale. But I want to emphasize these are model-based. They take the ocean color measurements and combine them with a model to produce these observations. Now, it's possible to actually directly measure primary production in the ocean using chemical sensors. This is work Rue Nicholson, for example, published in 2015 using gliders that would cycle multiple times through the day. So this is a daily cycle, 24 hours, oxygen concentration in the upper ocean. And you clearly see a diel cycle when you collect enough data. Oxygen going up in the day when photosynthesis occurs, decreases at night. This increase in the daytime is the direct measurement of primary production in the ocean. Now, this is a signal that is present everywhere in the ocean. Phase locked to the solar cycle, oxygen everywhere in the ocean is going up in the daytime. If we look at the entire Argo global data set in the upper 20 meters, we see a plot like this is local time, 0 to 24 hours, oxygen, highly scattered, but hidden in this signal has to be the same diel cycle of oxygen. And in fact, with appropriate signal processing, we can extract that. And here is the global diel cycle of oxygen derived from the global array, the entire array of biogeochemical Argo floats that are carrying oxygen sensors. We can find this diel cycle. We can take that and compute a global number for primary production from profiling floats. We get 39 plus and minus 9. This is the map of where the floats are located, and compare that to the satellite-based numbers. 39 agrees with some of the satellite measurements, lower than others, but this is a direct measurement. These are model-based estimates. There are also three-dimensional general circulation models with embedded biogeochemistry that have been tuned to reproduce primary productivity. And again, the floats agree with some of the models, are lower than others. The point is that we can now measure primary production directly. Now, this is the array of data we have now, large gaps in the array, but as I will say, we are moving towards the global system. We can fill this in and get really well-defined estimates of primary production. So Hervé, as Hervé said, we're now moving towards, we have demonstrated that we can operate arrays at a large scale, collect data and interpret it and do, transformative science at the global scale. The next step is really to implement the global 1,000 float array. Hervé has spoken to the plan that we've developed. In 1,000 floats, the model is that the US would provide half, as in the core Argo array, that's a 500 float array, and then observe the processes that Hervé mentioned and explore the application to management of living marine resources, carbon budget verification. And as Toshio stressed, all of this data is freely available in real time. And so in support of this plan, a group of US scientists wrote a proposal for the Global Ocean Biogeochemistry Array. And that proposal was funded in October of 2020. The National Science awarded $52.9 million for an array. This is a 5-year project to acquire 500 profiling floats with oxygen, nitrate, pH, and biooptics, and deploy these floats globally. The actual distribution will be coordinated with international partners as we attempt to reach the 1,000 float array, but this US program is now in operation. Partner institutions are Monterey Bay Aquarium Research Institute, the University of Washington, Scripps Institution of Oceanography, Woods Hole Oceanographic Institution, and Princeton University. These are the principal investigators and senior personnel. It's a very distinguished group of oceanographers with extensive experience in Argo and shipboard operations and interpretation of biogeochemical data, a group of people with a broad range of career levels from assistant professors up to very senior personnel that will carry this system on forward. And so GO-BGC is in operation. The first cruise deploying floats is at sea now in the Western Atlantic. 10 floats have been deployed so far on the cruise, 1 through 10. There are 2 more in the next week. And the array deployment, the global array has begun. GO-BGC will continue and with a focus in the subtropical and South Atlantic oceans. Next floats also will be deployed in the Eastern Pacific along the US West Coast and the Eastern Tropical Pacific, and efforts will continue in the Southern Ocean in coordination with the SOCOM program, which is continuing on into the future as well. So in summary, I would like to say the scientific applications of a global biogeochemical Argo array are clear, as Hervé has pointed out. The science is strong, we know what to do. The system is now with GO-BGC moving to sustained operation at the global scale. And the questions and much of the focus of this workshop is how do we incorporate a sustained data stream into ocean management, into fisheries applications, into carbon budget verification and validation efforts, and into forecasting future trajectories in the ocean with merged model and data systems. So with that, I'd like to conclude and pass on to Maria Hood, who is going to discuss the efforts from the G7 Future Seas and Oceans Initiative. Thank you.